Morning. Today's webinar is presented by Dr. Sean Santos from PNNL. It's my honor to introduce Sean to us today. So many of us are probably aware of Sean's multiple contributions to the E3SM model development, addressing issues in the parameterization of cloud microphysics, and more recently, the treatment of convective gaseousness across multiple components. Sean is a computational earth scientist. He obtained his doctorate in applied mathematics from the University of Washington in Seattle, with his doctoral research focusing on cloud process coupling in the E3SM atmosphere model. And that thesis work indirectly led him to rediscover the numerical instabilities in atmosphere land coupling he is going to discuss today. Sean briefly joined NASA GIS and became one of the developers of a family of data-driven cloud microphysics scheme called BOSS. And in 2022, Sean joined PNL and the Particle SciDAC project. The Particle SciDAC project strives to develop and apply advanced numerical methods to enhance the accuracy, stability, and efficiency of Earth system models, particularly those aspects that may benefit future versions of E3SM. And Sean's research with this SciDAC project focused on improved accuracy in cloud microphysics, parameterizations, and in atmosphere surface couplings. We are going to hear some of it today. Sean, please.
So I'm going to talk about primarily numerical stability and momentum conservation in atmosphere surface coupling, primarily focusing on the land, but near the end be potentially more relevant to ocean and sea ice. So the main issue that I noticed that sort of drove this study was that there's often these spurious oscillations in the near surface winds in E3SM. So what I'm showing here is the time series of winds for an example time period for an example point over Greenland. And you see E3SM V3 has this like sawtooth oscillation of the lowest level wind speed. And the period of this oscillation is twice the time step. So each time step it's going from low to high to low to high. Because of this, it was kind of immediately a question of, is this a numerical artifact? Because it's very suspicious that this is like the highest frequency oscillation you could possibly have in the model. And also, if you change the time step in E3SM to 3 minutes, that's this dashed green line for a run from the same initial condition. This is a few days in. So it's not quite the same mean wind, but you see that this oscillation is it's not existent. And just anecdotally looking at a few other columns, I was able to see that you might get some extra variability when you have a smaller temporal resolution at other periods, but you don't see this 2 delta T oscillation. So a little bit of history about this issue. I believe the first time this was noticed, having talked to Phil Rash about this, was sometime in Cam 4 or Cam 5 development. It was occurring over Antarctica. Anecdotally, it might have been noticed for other models that use explicit flux coupling before that. In those earlier lower resolution models, you could somewhat address this by using temporal smoothing or averaging. I believe in the release versions of CESM, they didn't even enable that because it was not too severe. I kind of rediscovered this issue during my doctoral work over South America, and it was more severe in E3SM V1 than in earlier CESM versions, which seems to be due to the higher vertical resolution in the boundary layer. There's less inertia, and so it's very easy, or much easier for you to get these big swings in the bottom level that's much thinner. And the issue persists in E3SM V3. Initially, I said here it appears less severe in tropics. That does seem to be true, but it's actually over the last couple days, I've done sort of a wider survey of different tropical areas, and you do see some areas where it's still pretty severe. So pretty much at any latitude, you can see this over the land. It's not really clear why there is some difference between V3 and V1, but it's probably either tuning differences or due to the gustiness bug fixes that were put into V3. These oscillations are common in stable boundary layers, particularly where the surface is very rough or the wind speed is very high. So over land ice, essentially the ice sheets over Greenland and Antarctica, also nocturnal boundary layers over mountains or forested regions. I don't see this occurring over ocean or sea ice, but I've mostly been running low-res F cases. So you can imagine for cases with very high wind speeds, like if you're actually resolving tropical cyclones, you might have this issue appear in that case as well, but it's sort of unclear. Haven't actually had the opportunity to look at that yet. So here's a map showing where these oscillations are most common. Basically using a Fourier transform-based diagnostic to look at where you have a very high power in that 2 delta t frequency of variability. This map, I should say, is on a log scale. So the very high end of this scale is essentially where that oscillation is comparable in strength to the signal from the diurnal cycle over most of the globe. And that's where you see like the very strong oscillations that are occurring here, where it's going from half of the mean wind speed to about 1.5 times. Anywhere where there's yellow, you get this happening at least occasionally, and the bluer areas, again, since this is on a log scale, it's basically absent. So in order to understand this, I developed a simplified boundary layer model. Because of time, I'm not going to go into this too much, but I did want to show this briefly if anybody's interested. Essentially what I'm doing here is I'm representing the winds as a complex number. One component is the real part of the horizontal winds, and the other component of the horizontal winds is the imaginary part. And you can write this equation, which is somewhat similar to what you might have seen if you've ever seen like the derivation of the Ekman spiral in a boundary layer with the Coriolis effect. And so setting up this simple equation allows this simple column model where we can study this kind of oscillation. So in order to do that, I showed the continuous equations, but you can modify them by only updating the surface stress, the lower boundary condition, at a fixed time step delta t. So that emulates the effect of E3SM's explicit flux coupling, where the land or ocean or a coupler is actually doing it for the ocean, but where those fluxes are only calculated and updated every half hour. So in those equations, you can actually analytically solve to find the maximum stable time step size. So if f equals 0, you can get this, the Coriolis parameter is equal to 0, you can get this somewhat nice formula. If f is not equal to 0, which is what actually the regime you care about for the poles, you can still get an expression, but it's too big to fit on this slide. It involves an infinite series, so it's a little less helpful. But there are some heuristics you can get out of this to get an idea of what the maximum stable time step size is. And it's also consistent with the observations that I mentioned earlier, that stable boundary layers with rough surfaces are where you would see this problem the most. So using this simplified model, you can also numerically reproduce the oscillations in this 1D model. So this is an example where for certain parameter values, you get these wild oscillations at a 30-minute time step. And as you reduce the time step, you eventually get the oscillations to be very damped and to go away entirely over time. This also gives us a test problem to try different numerical methods on without running the full model. So several modifications have been tried out here. So the big one that I'm going to focus on is this implicit method, which instead of calculating the surface fluxes based on the current atmospheric state, does it based on a prediction of the next atmospheric state or the next time step winds, effectively. And so in this case, there's sort of a spin up time step, and then after that, it's pretty good at damping the oscillations. That's this red curve here. There's also options where if you don't care about momentum conservation, you can just update the stress to sort of follow the winds within an atmospheric time step. And doing that also allows you to sort of damp out these oscillations, but at the cost of applying a different stress in the atmosphere to what was calculated and applied at the surface. So the implementation within E3SM required a little bit of consideration. Traditionally, implicit flux coupling has been used in models for at least as far back as the 80s. I'm not fully familiar with the history, but it typically is designed with a somewhat monolithic solve in mind. So a lot of the equations assume that both the atmosphere and the ocean or land are using the same time step size, that they're all using compatible semi-implicit solvers for the vertical diffusion. The atmosphere has to couple to other components in the middle of the PBL scheme. So there's a specific process order that's sort of enforced by that. And it's a little tricky to figure out how models on different grids with interpolations will interact with it. To get around this, I came up with somewhat of a novel predictor corrector design for implicit coupling. So in this case, the atmosphere generates a measure of the sensitivity of the boundary layer winds to the surface drag, effectively linearizing its own response to changes in surface drag. And it passes the parameters that come from this linearization to the coupler. And then the coupler itself for the ocean or the land model, calculating its own stresses, can then use this to estimate the winds that will occur at the next time step for any given surface stress. And then using this, we can come up with a nonlinear equation to find a stress and a next time step wind that are consistent with each other. And normally this would be a little bit tricky to do this nonlinear solve, but we already have a nonlinear solve going on in these models, which is used for the Monin-Obakov calculations to find things like the Obakov length and the friction velocity. And so essentially we can just add the winds as another, or the predicted next time step wind as another thing that varies over these iterations. And then this stress is given back to the atmosphere, and the sort of corrector step here is that it actually advances its own state using that stress. So with the explicit flux coupling, I'm showing you the same example as before, but now this red dashed line is the results you get with E3SM with this implicit stress method implemented. The oscillations are removed. The mean wind doesn't change very much. Also, it may seem like there's this gap between the 3-minute solution and this one. The sign of this difference is not very consistent. And also, the model is not really tuned to operate well for the low res at a 3-minute time step. So I'm not particularly concerned about this gap. But you see qualitatively, they have similar levels of smoothness. So that's kind of encouraging here. And then just showing on the map, this is similar to what we had before, showing where the oscillations are strongest. You can see that's essentially nowhere. These areas of the ocean, which really don't have any significant oscillation, the worst cases in the land are about the same magnitude. And just to compare, here's what I was showing before. This is what E3SM v3 looks like in terms of this high frequency oscillations. And then this is with the implicit flux coupling. I've also looked at the climate impact somewhat with, I think these are 9-year simulations that I'm showing here. So at the top here, there's temperature differences. And what I'm showing on the left is what happens if you just increase the number of Monin-Overkov iterations. So this is actually with the explicit flux coupling. All we're doing is allowing the implicit, or the Monin-Overkov fixed point solver to run to a larger number of iterations and probably converge a little better, which is something that's required for the implicit code anyway. So with this change, you get these somewhat mild temperature fluctuations. I'm not sure how robust these are for much longer simulations, but you do see a little bit of regional change, but not much in the global temperature. And then on the right here, this is the difference between, the difference between that increased iteration case and the control. On the right is the difference between the implicit stress case and the increased iteration case. And it's similar magnitude of change, probably a little bit weaker. And then here's latent heat fluxes, where there does seem to be a little bit of an increase in latent heat flux globally, but it's really, these are small changes. I should say this color bar here is, I think, 5 times smaller than the one in the E3SM diagnostics. So this would be close to invisible if I was showing you the E3SM diags, this latent heat flux difference. So we have similar climate and we get rid of the issue, so that's good. There are a few downsides. The two big ones, because the way that this is implemented involves running parts of club twice, basically trying to find this sensitivity to the surface stress in order to get this linearization information to send to the coupler. It has to run this, it basically runs this twice, one time perturbed with a different surface stress, and the other time being run with the actual surface stress. And so this is pretty small. It's always under 5%. There's some variability between machines, but this looks like basically a few percent extra. The bigger issue is that there's just a lot of extra complexity by adding a whole bunch of extra solves. So this is implemented for club. Porting it to something like shock could be a little bit tedious. So I am experimenting with a different sensitivity parameter calculation that's much simpler, basically using elements of a band diagonal matrix that's already produced in the vertical diffusion solver. It might be a little bit less accurate in the sense that we're sort of relying on the semi-implicit implementation and not looking at the sensitivity of the whole boundary layer code to perturbations. But it might be nicer to understand in the code and to port. In the interest of time, I'm not going to show too many results, partly because this is still running the, so I don't have like a very long to look at climate, and partly because short-term results look very similar to what I already showed. So my suspicion is that these will give pretty similar results. However, I want to point out that the initial implementations of this with the band diagonal estimator failed due to the next issue I'm going to talk about. And that is basically a method used within club, which is also present in shock as far as I understand the code from looking at it. And this method does not conserve momentum. And when I was trying to compare different methods to see how well they conserve momentum, I thought, well, this is a source of error. I'm going to try turning it off. But there's a reason that this is how this is implemented in the code. Basically, if you turn off this option, I got a crash, I think, within 10 months. So I'm going to talk a little bit about what the issue is here, and then really I want to encourage anybody who has an interest in this or has an idea or feel like they understand how to think about this, maybe to decide whether this is something that needs to be addressed in the code or not. So this method used in, I'm just going to talk about the club implementation right now. It's this option called surface momentum flux. It seems to start with the observation that basically by the definition of the friction velocity, u star, rho u star squared is equal to the surface magnitude of the surface stress. So if you assume that the surface stress points in the opposite direction from the wind, which seems pretty reasonable, at least at first glance, then you can invert this and see that the stress can be calculated from the friction velocity and the current winds. And once you write it like this, within the implicit solver, which uses the Crank-Nicholson method within club, you can treat this part in brackets effectively like a diffusion coefficient that's multiplied by the current near surface wind. You can add that coefficient into the matrix that's in the implicit part of the equation. And so that gives you the ability to apply the stress as something that happens to the implicit side of the equation, rather than applying the stress directly in a more explicit way. And again, this enhances stability. So there's three issues with this for momentum conservation of the whole system. The first is that the way that this is currently implemented is it's mixing these values from different time levels. So this part in the square brackets uses the current time step, and this other part is effectively, in the implicit method, the next time step wind. This is not necessarily a bug so much as a trade-off. I believe this is basically why this implementation is more stable, but you're trading off momentum conservation for stability, because now the atmosphere is modifying the stress and it's not applying a stress that's equal and opposite to the one passed to the ocean, effectively. Over the land, this could be an issue, except we don't really care about momentum conservation over land. The land is an infinite sink of momentum, effectively. The second issue is that by the time that you get to the part of the atmospheric time step where club or shock runs, the wind has been changed by the dynamics and possibly by other schemes. And so the wind is not necessarily the same value as it was used to originally calculate the surface stress. And so the stress might not actually point in the direction that opposes the current direction of the wind. So that assumption is not quite correct. And then third, you're assuming that the motion of the surface is negligible compared with that of the atmosphere. But you can think of, like, say, you have making up some numbers. If you have an ocean current that's moving 2 meters per second, atmosphere is moving 1 meter per second in the same direction, the ocean would actually pull it in the same direction as the wind is pointing. Again, I don't know how large this effect is really, or how common a scenario like that exists, but it is an issue here. So I just wanted to bring this up, partly because I'm just curious whether this is something that we do need to do anything about. It's very straightforward in the code to measure this momentum conservation violation, but we don't really prioritize conservation of momentum in the same way as energy or mass. As somebody who mostly works in cloud physics, I don't really know how big of a violation you need for it to really be a serious issue. So it'd be nice to have, if anybody has any feedback on that. There are some options that we could take to try to change this. We could try to improve the stability in the model in some other way, and then just stop using this implicit code effectively. But that might require making the boundary layer more diffusive, or extra cost from substepping the calculation. Another thing you can do, which might be sort of the easiest change to make, would be to modify this method to account for movement of ocean and sea ice. So you would still maybe be momentum non-conserving, but you'd at least get rid of this third issue here. And then the fourth issue is, or the fourth possible solution is, since you can easily calculate how much you've violated conservation of momentum, you could implement a post hoc fixer that either distributes that extra momentum through the atmosphere or sends it back to the more massive surface component, which might be able to absorb it without causing any major issue. So in conclusion, we have these high frequency oscillations in E3SM v3. These do seem to be due to numerical instability involving explicit flux coupling, and we're able to study this in a simplified model. A predictor corrector implicit flux coupling method has been implemented in v3 already that can remove these oscillations without big changes in model climate. But there's some momentum conservation issues with the current code. Those are trickier to solve potentially. So with that, I am done. I want to thank the SciDAC 5 program for funding us so well, and I'll take any questions.
All right, thank you.